Okay, so hi all. So this video will just sort of pick up where we left off in class on Wednesday, which was in coming up with our first method for solving ODEs. I think I said this in class, but I'll just repeat here. This video course should hopefully be pretty much just like in class, obviously, except without seeing me. But this is sort of the same setup. So I just sort of recommend you do the same thing we do in class, whether you're in person or zooming in. Take notes from this. Obviously, you can rewind or pause this as opposed to real life. So that could be good. Please do watch this whole video from start to finish. I know it's tempting to kind of zoom ahead, but I know there's plenty of stuff that I say that I don't write down. So please take the 15 minutes that we would normally have in class on Friday and watch this at some point over the weekend. We'll get to our second method today, which is the last thing you need in order to do the homework. So you should be able to do that over the weekend. And I should say, as we're going through this, obviously, if you have any questions, just jot them down. Maybe jot them down in your notes, and you could either send me an email or just ask me next week, and we can chat about whatever. So, okay, so I'll do a quick recap of the end when we sort of ran out of time in the middle of a example here, but I'll give you the recap of our first solving strategy for solving an ODE. So it's just called separation of variables. So what does this entail? So if we have our ODE, and a first thing that we might try to do is that whatever format the y prime is in, I mean, if it's in this format, for example, you want to convert it over to the fractional format, so dy over dt, just so that it's already a fraction, which is going to help us to do the next step, which is to separate the y's on one side and the t's on the other. And that includes the d stuff, so dt and dy. Those have to go with the t's and the y's. Typically, we put the y's on the left and the t's on the right, which we'll see when we do our example y. That's usually true. So we separate. We get all the y's on the left and all the t's on the right. And then it's practically begging for you to do step 3, because the left side and the right side will both just look like integrands. Right? Integrands meaning things that we are used to putting an integral sign in front of and doing an integral. Right? They've even got the dy and the dt, like usually, in Calc 2, we'd write an integral and it had a dx at the end of it. So these will even have those, right? So it's almost sort of saying, well, gee, you have an equation and you've got two integrands, why not integrate? And the reason, of course, we'll do that is because some y's are going to appear, and hopefully just one y. But we'll deal with what happens if you have more than one. But remember, the whole goal of this whole thing is to solve for y. Y is our big mystery function. I don't know who y is at the beginning of these ODEs, but my goal is that at the end of it, we can write down something that says y equals, which would mean, hey, we found the solution to the problem. All right? Now, when we solve this, we're going to get, we're going to do these steps, right? And we're going to get a solution. That's the general solution. So if you remember from our first day, the general solution is an expression that represents all the solutions to the ODE. Remember when we were playing around with, gee, can I solve this? Can I not solve, can I do these sort of just by thinking? We came up with actually the case that when we're trying to solve, we actually have a whole family of solutions. That's called the general solution. And there's going to be a c in it, which we're going to get from doing an integral, but represents sort of I'm not sure exactly what this is. This could be any number. So what's going to happen is when we solve these in any strategy, not just separation of variables, we're going to get the solution y equals, hopefully. But then there is a last step that we will do if we have what's called an initial value. So I didn't jot this in on Wednesday, so maybe hopefully have a little bit of space under D to say E, or the last step for all ODEs, not just separation of variables, but all ODE problems, is that if we have an initial value, we can use it at the end to solve for C. So I'm going to write that down. So if we have an initial value, and by that I mean we're given that y at some time is some value. Now typically t0 is 0. So in other words, we're usually saying y at time 0 is, 7 or whatever the value might be, right? So if we have that in the problem, and I'll show you where it's usually kind of written, then we can use it at the end to solve for C. So we can run it through our general solution to solve for C. Okay, so jot that down. This is a very easy step to do at the end, so we're not going to stress out about it. All right. Now, we don't always have an initial value. Some of the homework problems, they'll give you one. Others, they won't. So if you don't have an initial value given to you in the problem, then you just don't do that step. You just, you stop at y equals whatever you got, and that's it. Okay. All right, so let's revisit the one example that I didn't quite finish this on Wednesday. So we had this ODE, y prime equals y minus 2. Now, if we had an initial value, which I didn't fill in on Wednesday, it would typically be sort of written over here. So it might say something like, I don't know, like that. Right, y of 0 is 4. And it's usually just written off to the side like that, right? Maybe with a semicolon or something like that. Okay. So, all right. So we solved this one on Wednesday, but I'll just give us a quick recap. So we solved this using separation of variables. That's the only strategy we know right now. So what did we do? We took step one was we rewrote y prime as dy dt. Okay. And then what's nice about that is that you have a dy now and a dt, and it's sort of hopefully begging for us to put the dt on the right side just by cross multiplying. And I'll move the y stuff to the left side, in which case I ended up here. So I've separated at that point. I've gotten everything that has a y. And the number, you might say, well, what about that minus 2? Well, numbers can go anywhere. They could be on the left or the right side, and they're going to be just fine. Okay, but the y's have to all get to that. Okay, the t's have to go right. All right. So when I'm here, I say, well, this almost looks like an integrand, or in fact, these each look like integrands. So how about I just perform the integral and see if that moves us towards a solution? Right, it's a reasonable thing to do. So I did the integral at the end of class on Wednesday, and I ended up with ln on the left. That's a u substitution. Do that slowly if you need to, but that'll turn into ln of y minus 2. And on the right, the integral of 1 is just t. And of course, we always are going to be very careful to remember the plus c. We need the plus c. Now, you don't have to put a plus c on both sides, or like a c1 on the left and a c2 on the right, because as long as you just allow for an arbitrary number to be added in somewhere, you're good to go. Right? Usually you put it on the right side. Usually you put it with the t, because my next step is going to be to make this read y equals. So it's better to leave the y side as simple as you can, and we don't really care if we mess up the t side a little bit. Okay, so we ended up here. But then we said, oh, all right, well, I want to make this read y equals. Well, the y in this case, which remember, that's our solution. This is the hero of our story is y. We need to free it. It's in jail right now. It's trapped inside of an ln. So I want to get that out. And if we remember from pre-calc, the way to get rid of an ln is to e it, right? Or to do e to the power of ln of stuff. And when I do that, e and ln, I don't want to say cancel, but they essentially they do. And so I'm just left with y minus 2. And on the right, I've got that stuff. Okay? And then I just moved the 2 over, and that's how I got my answer. Okay? So, so that was, we stopped here, right? So, but I wasn't actually quite finished yet. We just ran out of time. So, but that's our general solution. But I've got a little bit of tidying up here to do. So let me finish this. So now algebra would say e to the t plus c, when you have a sum of exponents, that's the same as having them separate, written this way, right? So e to the t times e to the c is the same as e to the t plus c. Now that's usually we do that the opposite order, but in this case I'm splitting it apart because now we're going to tell ourselves a little story, which is, so c, what is this c? Remember, c is any number, anything you could imagine. It's positive numbers, it's negative, it's fractions, It's even pi, right? Irrational numbers. It could even be imaginary numbers like I and stuff like that. So C is just any possible quantity of any sort. So what is e to the c? Well, if c is just anything you could ever imagine, then e to the c would also be anything you could imagine, right? The fact that I'm doing e to something, right? E is just a number, right? It's 2.71 something, 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 right? So if c itself could be any value, e to the c could be, this is just any, whoops, what did I do? Okay. This is also just, this is any value, e to the c, right? So why am I making a big deal about this, right? And if we were together, I'd be, acting this out and doing, a puppet show or something about making a big deal about this. Well, because if c is any value and e to the c is just another way of saying, well, that's also just any possible value, then why am I going to bog us down with saying that that's e to the c? Why don't I just make up a new constant and say, since this is any value, just make up a new constant. And you know what my new constant's called? C. Now that's a little bit funny, right? Because I shouldn't probably use the same letter. I should probably use K or something like that. But we're so used to seeing C meaning any possible value that we're essentially just renaming e to the c, C. Or new C, if you'd like. Okay? So that now is our general solution to the ODE, right? Y equals 2 plus c e to the t. So that describes all the possible solutions, right? So this ODE up at the top here, we actually did the graph of this one the other day. And sure, we traced in those little curves. There's a lot of solutions, right? Because it all depends on where you start. You get a specific solution. Oh, sorry, I erased my little bit over here. Right, so this describes all the solutions, all the curves, and so that's nice and that's good. In a lot of cases, that's all, if we had nothing else at the end of the problem, I would just put a box around this and say I'm all done. But in this problem, we do have, sorry, I erased it a second ago, but we were given a point. In this case, this is basically just saying when time is 0, y is 4. Or we could say the initial value of y is 4. I'll go back to my temperature example. You're doing a chemistry experiment, and you're starting with a y value of 4. It's a way of thinking about that. So this describes all the solutions here in the box, 2 plus c e to the t. But if I specifically want the one that goes through 0, 4, I can run this point. I'm going to squeeze this in at the bottom here. Right? I can, at the very end of my problem, take this initial value, as it's called, and I could run it through my equation, and I can solve for c. So let's see what happens. So this says y is 4 when t is 0. Right? That's what that means. Oh, well, e to the 0 is 1. So this is saying that c is 2. Ah, okay. So the general solution is in the box there. But the specific solution that goes through the point 0, 4 has a c value of 2. All right, so I ran out of space down up there at the bottom, so I'm going to put my answer up here. And I'll say, so the specific solution is y equals 2 plus, but now instead of c e to the t, I can say 2 e to the t. All right. Okay, so we solve for c and then fill that in our general solution, and that gives us the specific one that starts at 4, is how I might say that, right? Okay? So one last thing that we might do at the end of the problem, I'm going to just copy that down again. So we have a general, right, general solution was 2 plus c e to the t, and our specific solution is 2 plus 2 e to the t. Now at the end of this, we might ask ourselves, or I should say, I guess the book or the homework problems may ask us, oh, could you tell me what's happening in the long run? So a typical question we get at the end when we solved, especially for a specific solution, is to say what's happening to the solution as time goes on, right, or in the long run. And that's basically just asking, tell me about the y values when t gets big. Okay, so I think I reminded you in our little calc flyover of a thing called limits. Now, you don't have to be super fancy and bust out crazy notation or anything like that. But yes, technically this is asking at the end of a problem, you're going to see a question like, what's happening to the, we'll say to the specific solution in the long run, which might be written as t goes to infinity, right? Or it might just say in the long run, something like that. Okay, so don't freak out about this. This isn't saying much, right? So here's our solution. So all you have to do is ask yourself, well, gee, if t was big, what would this look like? Well, if t is big, then of course e to the t is like uber big. Multiplying it by 2, still real big, and adding 2, still real big, right? So in this case, right, this isn't the most exciting question, because as t gets big, this whole thing, every single piece of this is just getting big. Well, actually, just the second piece, right? 2 is just 2, right? So, well, I would say at the end here, right, as t gets big, y also goes to infinity. So my solution here, right, my solution blows up, right, goes to infinity. I don't have it in the same group of slides, but if you flip back a few pages in your notes, when we did this, the directional field for this ODE, it was the first one we drew. I think we ended up with a graph. Oh, geez, what am I doing there? I think we ended up with a graph that looked. We had something like this, I think, right? I think that was sort of what our directional field looked like. And this was 2. So what's this saying? This, for this specific solution, which started at 4, we probably drew a little arrow pretty much right near 4. And I bet you it looked just like this one, that it goes up. And isn't that exactly what the graph of e to the t looks like? And it is. And if you type e to the x in your calculator, you get a graph just like that, right? But indeed, it goes up to infinity. We said that in class. And look, so does this one, which should make sense, right? This is the exact solution, right? We were just drawing little sketches earlier, were sort of just approximations of the solution. These are the actual solutions now that we've done. So it's nice that they agree, right? And they match. Okay? All right. So that's one full example, all the pieces done. I'm going to do 2 more, actually, using separation before we move on to another strategy. Okay, so let's try this one. Y prime equals ty squared. Okay. So we want to solve this, right? So of course all these questions say solve the ODE, right? And we only have one strategy so far, so I'm going to keep trying separation of variables. That's our only technique so far. So separation of variables says we'll start by writing y prime as a fraction, dy over dt. And again, that hopefully motivates us and helps us see, oh yeah, this kind of looks like if I move the y's to the left and the t's to the right, I could separate. So if I move y squared over here, and then dt over here, I've separated. So that wasn't too bad. So hopefully this is begging for us to now do an integral, because it already looks like it's an integrand, or 2 of them. So let's integrate. The easier integrals on the right, you get t squared over 2, plus c, don't forget the plus c. Now on the left, let's see, what do I have? I have dy over y squared. Of course, y squared on the bottom is really y to the negative 2, I guess, right? That would be the best way to think about that. And the integral, and that you could just integrate like regular, right? Y to the negative 2, I'd add 1 to the exponent, so that's y to the negative 1, and then divide by negative 1. So I think I'd end up with negative y to the negative 1. All right? Do that more slowly if you need to, or do the rewrite, but hopefully we're still pretty sharp with doing integrals. So I think we'd get negative y to the negative 1. All right. Now, my last step in solving the general problem is to make this read y equals. Now, the next example I'm going to do, we're not going to be able we're going to sort of crap out and not be able to do it. But this one we can, right? I can rearrange some terms here and get this to actually read y equals. So in order to do that, well, negative exponents are not our friend when we're trying to do just algebra. So instead of y to the negative 1, I'd actually be much happier just thinking about that as 1 over y. So that's nice. And now if I want this to read y equals, you could say, well, you got to flip, right? You could flip both sides, or, you know what I mean, just invert them. And at least that would make the y go on top as long as I put the other side on the bottom. Or you could say you're cross-multiplying or swapping or whatever you want to say. But I think, well, hopefully all roads would lead us to saying, well, I'll put the t stuff over here. And so that enables me to put the y over there. Again, or say, flip them both, right? Flip both sides, that works too. All right? And so just to clean this up a little bit and move it up here. So I think our general solution is y equals negative 1 over t squared over 2 plus c. Okay, sorry, and I meant to fill in an initial value here that I forgot. So let's throw that in so we can get practice doing the solving for c. But there's our general solution. Now, I can't do any funny business with the c here. In the last problem, I did, right? I said, oh, e to the c is really the same thing as a new c. Well, where the c landed when I got to the end of this thing is that it's on the bottom of the fraction. I can't really liberate that. I don't know exactly what I would do with it. I can't, move the c to the top or anything like that. This c is kind of stuck where it is. So I can't really do anything fancy at the end here to move it around or make a new c or anything like that. So I'm just going to leave it be. All right. So that's the general solution. Okay, that's nice. All right, and then maybe now I want a specific solution. So to get a specific solution, I just use my initial value and run it through. So that says when t is 0, y should be 1. Okay, so y should be 1 when t is 0. Whoops, squared. Okay, so that's, of course, just 0. And so what do I end up with here? I get 1 equals negative 1 over c. And so c is negative 1. Okay, so my specific solution is y equals negative 1 over t squared over 2 minus 1. Okay, and we'll ask and answer the same question again. As time goes on, what's happening to our solution, our specific solution here? Well, again, I'm just going to ask myself, play the little game here, right? As t gets big, what's happening to everybody? All right. Well, as t gets big, well, I only have one t in my problem. It's here, this t squared. So, of course, as t gets big, t squared is big. And t squared over 2, well, dividing by 2 doesn't do, that doesn't really have much effect on infinity. So this is still, so that's real big. Now I'm just going to subtract 1, who cares? It's still real big. So what's negative 1 over a real big number? So this is where, just think about it for a minute, right? A regular number split into a cajillion, billion, trillion pieces. means each piece is essentially 0, or is very small anyway, right? All right. So I think as time goes on, this whole fraction here is heading towards 0. Okay? Right? -1 over infinity, which is 0. So as time goes on, the solution's dying out, you could say, I guess, if you were trying to put this in sort of a word problem. It's saying, oh, okay, well, essentially you end up shrinking down to 0. Right? Now, of course, if you chose a different c value, sometimes it depends. In this case, I don't think it's going to really matter. But in some cases, you might get some wildly different behaviors. Right? Okay, so that's a good second example. And I'm going to do one more for you, where I don't think at the end we're going to be able to actually solve for y. And also I'll leave this general, so no initial value. But let me write it down. So y prime maybe times y plus 1 equals e to the t. All right, so there's our ODE. Okay, so, well, let's see. I got to separate. So I'm going to rewrite y prime as dy dt. Y plus 1 equals e to the t. And now to separate, maybe I'll leave the y's on the left, and all I have to do is swing that dt onto the right. So just to make this look a little nicer, I'll say that's y plus 1 dy, and e to the t dt. All right, so that was pretty easy to separate. So now that I've separated, I'm ready to integrate. Okay, as usual, the right side is easier. E to the t, that's my favorite. That's just e to the t, but remember the plus c. Now on the left here, this is also an easy integral, right? Y plus 1. Remember, dy tells you that y is the variable, or think about y as a variable. Oh, this is pretty easy. Y plus 1. Y turns into y squared over 2, and 1 turns into y. Okay, that's pretty good. Okay, so now, so I've done sort of steps 1, 2, 3, 1, 2, 3 anyway. Okay, usually I like to see if I could make this read y equals. Now, here's where we have to pause for a minute and look at this and ask ourselves, am I going to be able to get this to read y equals? In general, you're in big trouble when you have more than one y, because unless they sort of go together, or in some way that you can, I don't know, factor them or group them together, you're not really going to be able to make this read y equals. I mean, by the way, this doesn't count. That's cute. I guess it does say y equals, but, oh, oops. You got y's over there too, right? So that's not good form, right? So that's no better than what we had before. So I don't think I can do that. And if you try for, 10 more seconds, you're going to quickly give up. And good, right? Because I can't make this read y equals. So the best I can do, so I'm not going to get a nice y equals blah, blah, blah at the end. But the best I can do is say, well, all right, this at least describes my solutions. It doesn't tell me exactly who y is, but the mystery y that I'm searching for is the one that works in this. It's a little disappointing, to be honest. But so how should I leave this? I don't care if you would leave it just like this is fine. However, I think the WebAssign, when you do the homework and you end up with ones like these where you can't make them read y equals, they like you to put it in the format c equals. In other words, the constant equals. So that's easy, of course, right? I can just move the c or we'll just leave the c alone. Right? So I'd say, oh, okay, so y squared over 2 plus y minus e to the t equals c. So that's going to be my solution, my general solution. And I'm just going to leave it like that, because there's really nothing more I can do. Now, if I did have an initial value, I don't know what's happening with that. If I did have an initial value to plug in, I could still run it through, and I could still solve for c, right? I could still do that. Right, I'd plug in a value for y, plug in a value for t, and it would tell me what c is, right? So that doesn't stop me from doing that. But it does, but right, in no format am I going to be able to make this read y equals. And this is a little hard to do the limit at the end too, because you got y, anyway, so you don't worry about that for these problems either. Okay, but we still got to a solution, so that's reasonable. We were still able to separate. All right, now I said I was only going to do 3 examples, and I mean it, because I'm going to write a 4th one up here that we're going to punt on, because we're not going to be able to do it. But let's at least start. So the other example that we did the graph of on Monday, I guess it was maybe, was this ODE. This was the one that had the directional field where there was a line, an equilibrium line that sort of appeared, which was kind of neat. Okay, but that was just us sketching. That wasn't actually us solving this. So let's try to solve this. Okay, so I start, as I usually start with these. I say, oh, well, I'm going to do separation of variables, so I'll write this as dy dt. Okay. And now, as usual, I maybe want to get the y's on the left side and the t's on the right side. Okay, well, let's see. I can cross multiply and get the dt on the right. Okay. Okay. But now I need to get the y's on the left. Well, I have the dy on the left, but I got to get this guy over there. Now, if there was no dt attached to it, I could subtract, or I guess add, and move it to the left. But that dt is times both of them. Well, that's not good, right? And maybe just to remind myself of that, if I distribute the dt, okay, I got that. Well, this I'm okay with that, but ooh, that looks bad, right? That needs to either the t part I'd like to keep on the right, but the y part I need to get on the left. Ooh, okay. So this is a good example of a problem that is not separable. So I can't do separation of variables because no matter how much algebra you try, you're never going to get the t's and the y's to be separated from each other. All right? So this fails, right? So this is not separable. Okay, so we're stuck, basically, right? Because I only had one strategy. I don't have a second one. So I'm not sure how to do this. Oh, and of course, right? I mean, this isn't even that complicated of a problem. Of course, there's going to be lots of examples that don't separate. Okay, so we desperately do need a second strategy. All right, so our first method was separation of variables. We like that. But here's going to be our second method. So I don't know where I am with numbering and stuff. Oh, wait. Okay. Oh, you know what? We'll just call this method 2 just to make sure we're clear here. Okay, so our second method is called, has a couple of different names. Integrating factors. It's also just sometimes called a linear ODE, although that's sort of an overused term. So I'll stick with integrating factors. So that's going to be more descriptive of how we're going to solve this. So let me give you the idea first, and then we'll see what we can do about this. So our second method here, called integrating factors, says the following. So if we can't separate, as we just saw in that example, then how about let's try this. Then we may be able to, in fact most of the time, write it in this format. Okay, so y prime, and then maybe I have some stuff with t's times y, and then maybe I have some other stuff with t's. Okay, so when we say stuff like this, right? Sorry, that's a T. What is little f of t and what is little g of t? Some stuff with t's. Sine of t, t squared, 6 plus t, I don't know, whatever we got. Okay. So chances are, if you can't separate, what's the issue? I mean, if I was gonna try to say what was so different about this one that we got stumped on, it's that you have 3 terms. You got y prime, t, and y. That makes it very difficult to separate, right? So like this one that we did before that, I had 3, well, I guess I have several pieces here, but I have multiplication, right? The left side is just 1 term, and the right side is just 1 term. So that's what enabled me to do the separation. But if I look at this one that we got stumped on, I have 3 individual terms, which is why it was really tough to get them together. So as you can see, this method is actually sort of made for when you have 3 terms, and in particular, 1, 2, 3. Okay, so if you can write it like that, which most of these you may have to do a little bit of rearranging. Then is there a way to solve something that looks like this? And hopefully there is. Otherwise, I'm wasting our time here. So, and there is, right? So if we can rewrite our problem like this, then here's a neat trick that we're gonna do. So if we can't separate, we can write our ODE like this, and then what are we gonna do? Then we can multiply the entire ODE, meaning left side and right side, by what's known as an integrating factor, which is just a fancy name for an unknown, I like to call it helper function u of t. I don't know why we always use u, but usually that's the lettering that we use. Okay, so far this seems like I'm just chasing my tail here, but there's going to be a good reason for doing this, I promise. So what's the integrating factors approach say? Well, it says, first of all, make your ODE look like this format here that we see. Y prime plus f of ty equals g of t. And then let's multiply the whole thing through, for some reason, by some unknown helper function known as an integrating factor. At first this is going to seem like I'm actually making the problem worse instead of better, but I promise it's actually going to be quite helpful. All right? So I start with this. Step 2, multiply through by my integrating factor. Okay, well, all right. So I'm going to take my u, and I'm going to multiply the whole equation by that. Okay. All right. And now I'm really getting suspicious because I really feel at this point is that I've just made this even worse, right? I don't see really how this is helpful at all. Until we make a very, very clever observation that somebody made a long time ago, which is that when I look at this guy, when I look at let me get my pointer here. Right, so when I look at this guy on the left here, right, don't worry about the right side for now, so let's just, pretend that's not there for now. But when I look at the left side of this, now you're going to have to squint really hard to naturally sort of see this. But what do I have here? So if we look at this whole left-hand side here, well, in particular, if we remember, let me jot this down in the little side over here. If you recall from Calc 1, the product rule for doing a derivative said if you have 2 functions multiplied together, you remember the product rule tells you how to do the derivative of a product, right, of these 2. So let's say I had 2 functions, maybe I'll just call them u and y. I think probably in our derivative chart we called them f and g, but that's okay, right? We'll call them u and y for a change. Then if I wanted to do the derivative, right, we had the product rule, which told us that the derivative of u times y was the following. The first times the derivative of the second plus the second one times the derivative of the first. Right? That was the product rule. Okay, so that's old school. That's Calc 1. Now, why did I just remind you of that? Well, now is when I want to do some analysis here. So, stare at that and stare at that. Now, it's not a perfect match, but actually, 3 out of 4 pieces are perfectly aligned. So I have uy prime. I got a y over here. I got a y right here. Oh, now the only piece that is not, magically perfectly lined up would be those pieces. But if they were lined up, it's still not clear why this is a good thing. But if they were lined up, I could, instead of having this hot mess of stuff over here on the left, right, this stuff, instead of having all that, I could just have u times y prime. Now maybe that doesn't seem that exciting right now, but that's actually going to lead us to a very easy way to then solve this ODE. All right, but let me write some of this down so I'm not just saying this. So just by observation, let me clear out some of my inking here. So as a comparison to the product rule, right, so we notice that this matches. Let me actually just leave that one there. Right? Everybody else is good already. Right? So we notice, right, this matches, or maybe I should say this will perfectly match the result of the product rule if we insist that the one piece that is not already lined up does line up. So for that, all I'm going to say is let's match up our 2 blue circles. So if we insist that u prime be f of t times u. Okay, and that's step 3 of this process. I'm going to go on to the next slide to write that down. Okay, but just, we can all stare at this for one more second, right? So I know this seems like a strange thing to do, right? But, well, so far, right, all I'm doing sort of is saying, well, I don't know how to do this, right? Because I don't, right? I don't know how to do this problem from the get-go. I don't know how to do this. So I got to try something. So I'm apparently just sort of by observation and memory thinking, gee, this kind of actually looks like the product rule. And as long as I can guarantee that that's true, it'll actually be exactly the product rule. So that's how we're going to proceed. So let me switch back to red here. So step 1, get it in that format. Step 2, multiply through by our mystery u, our helper function known as the integrating factor. And then step 3 is let's insist that u prime be, oh, I forgot my letters now, f of t times u. Now, what does that do for me, I guess, right? So far I've taken a problem I don't know how to do, I've made it worse, and I have a new problem that I'm not really sure how this is helpful. But now, if this is, so I'm going to insist that this be true. However, this ODE, so I just wrote down a new ODE. That's why? That's an ODE for u, because I have u prime, and I got some t's floating around, that's fine. But this is going to be a separable ODE. All right, so let me say that first, right? Now this is a separable ODE for u, or u of t. And separable is our favorite word, because we know how to do those. All right, in fact, what do we get? Since this is separable, let's separate. All right, how do we separate? We rewrite, right? So it's just that it's an ODE for u, right? Instead of y, this is just a new thing I came up with. But u is a function also, so this is an ODE for u. So u prime is really du over dt, and over here I have f of t times u. Oh, and look at how this separates pretty nicely, actually, right? So if I move the u to the left and the t on the right, I'm going to go sort of horizontally here. So then I have du over u, and here I have f of t dt. Sorry, I don't know why my u's look weird. Well, I separated, so I could do an integral. And if I integrate this, I'll keep going here, I get ln of u on the left, du over u, that's ln. And on the right, well, I don't know what that is, okay, because I don't know how much f of t is. And then in order to get u, I could just e both sides. So let's separate and solve. And if we do that, I think we end up with u is e to this integral. Okay, so let me draw an arrow here to say, right. So of course, how would I make this say u equals is our usual trick. How do I undo ln? I e it. Okay. Again, this is all seemingly just an exercise, and now I've really gone off the deep end because I have no idea where we're going with this. But here comes the good part. All right, so I can do all this. This looks like a lot of work, but I can do this. Okay, all right, I can do that. Remember, f of t, that's just whatever was here in the ODE, right? So, right, it's part of the original ODE. So you know what f of t is. Well, hopefully it's not too bad. Maybe it's just t, or t squared, or I don't know, something like that. So doing that integral, it's not the end of the world. Okay, then I get e to that as my u. All right, fine. But now why is this actually a very good thing? So you'll solve for u, and you get whatever you get. So now, though, now that I know what u is, now going back to the original ODE, what do we have? So let me just flash us back here. Or so maybe I should say, going back to step 2, I guess I should say. So going back to step 2, what do I have? So this whole left-hand side, and we've forced this match to happen. That's what the u is for. So this whole left-hand side here is actually just u y prime. So if we go back to 2, maybe I shouldn't say back to the original. So going back to step 2, we now can fill in the u that we just computed. Okay, I guess I'll call that step 6. I shouldn't have started numbering these because it's going to look like there's a million steps, but they do sort of just flow after you do one or two. So if I go back to step 2 now, right? So step 2 said I had all this stuff on the left, but it's actually just uy prime now, and that's equal to u times my original g of t. And why am I basically done now? Well, I'm not 100% done, but I'm pretty close to done. Because now what can I do to finish? Finally, goodness, step 7. If I integrate both sides, then we get, well, the integral of a derivative, those are opposites, right? So the integral of uy prime is just uy. And again, I'm not sure, I can't tell you specifically what this is yet. But you could do an integral. U is just, u is u of t, right? So u has some t's. G of t has some t's. So I do an integral. Well, whatever I get, I get. And finally, I do mean it, in our very last step now, I need to make this read y equals. So the only thing I need to do to finish this is divide both sides by u. All right? So my last step is, finally, then the solution, the general solution, is attained by dividing both sides by u. So we end up with y equals, I'll just copy this stuff down, right? So I divide both sides by u, so I get that integral thing there. The integral of u times g, all divided by u. And that's going to be the solution to the ODE. Whew, okay. So that's a mouthful, right? I should put some sort of box around this. So before I hit stop on the video, okay, wow. So there does seem to be quite a bit of work here. At least there's quite a few steps here, I should say, I guess. But it's actually not all that bad. They will sort of flow into each other. And what do I actually need at the end of this? All I need to know is u, right? That's part of my solution here. Well, we have a strategy for that. U is attained by doing step 5. Okay. And I have to know G. Oh, but G is part of the original question. Yeah, it's right here. So I have U, I have G, I know how to integrate, I know how to divide. This feels like a thing I could possibly and probably do. All right? But obviously we do need to see this with an example in front of us so we can see the integral and all the steps and all that good stuff. So, but we'll do that on Wednesday next week in class. So you can mostly do all the homework. This is all you, if you want, you can play around. I've shown you all the stuff you need to do, but if you want to see an example or two, we'll do an example or two on Wednesday. In class. So the homework number 2 will be due Friday of whatever that date is, Friday of next week. But do get started over the weekend. If you wait until Wednesday or Thursday night to start this, it's a long homework assignment. There's a lot of problems and you can basically do all of them now. So please do get started so that when you run into trouble, you still have some time to figure some things out. But we'll pick up with this on Wednesday, and I'll do examples with this, and hopefully this will seem a little less scary. Even I'm a little bit intimidated by how many steps it seems like it is, but it really is honestly not all that bad. So, all right, so have a wonderful weekend, and these notes I'll add to them on Wednesday with our example. And have a good weekend. There's, of course, no classes on Monday for President's Day. So I'll see cohort A. I'll see you in class on Wednesday.